Karen. I'm the Higher Education Manager here at UCM. And UCM Talks is one of our community initiatives to reach out and encourage and informed debate. And tonight's talk is from our very own Dr. Ali Robertson, who's been with UCM now since 2011. Prior to that, you're at the University of Lancaster, where you did your PhD and also started your lecturing career at the University of Lancaster. And we're really blessed, as we are with many of our lecturers, to have someone like Ali, who's not only a good educationalist, but is developing new concepts, new ideas, and continuing with his own research. And I'm going to say some things now that I don't completely understand. However, he is a primary lecturer in our computer science program. He specialises in statistical methods and machine learning, and how that shows up in his life is that he has a role in life as a data and analytics consultant, and he's also a machine learning systems writer. So you're actually out there giving things to the world.
I can make these things, yeah.
You can make these things.
Yeah, I can write about them as well. Yeah, I'm an author. So.
And what he wants to do tonight is, we're all aware of the challenges the information age has, or the challenges and the changes that the information age has given to our lives. But Ali's going to specifically look at what that means for computer science curriculum, how we bring machine learning and artificial intelligence into the classroom in a useful and productive way.
Yeah, that's a good introduction.
All right.
Yeah, it's nice.
Thank you, Ali.
No problem. Thank you for coming tonight, actually. In some ways, I like the small numbers here. I prefer when I'm teaching, I teach throughout this number of people, and it's really good. You can always get a two-way conversation going with people around here. But I've got a couple of apologies before I start, because my title is somewhat different than that was advertised. I think what was advertised out there was artificial intelligence in tertiary education. I've actually, as I'll highlight, artificial intelligence isn't really the game for us here right now. It's more about the machine learning at the moment, which leads us into artificial intelligence. But one of the punchlines that I'll come to later on in about 40 or 50 minutes, maybe a bit earlier than that, is actually, without good machine learning, you can't have artificial intelligence, full stop. It's a fundamental requirement, almost, of good artificial intelligence. But I'll roll those definitions out as I start talking about them. In my youth, my father had a collection of Isaac Asimov books. There's one there, I, Robot, produced probably around about the 1950s or 60s. This epitomises for me what computer science is for humanity, what it should be. It doesn't always get there. Which is, there's a robot. We didn't have robots, only barely had computer technology at the time when that art was created. Doing what technology should be doing, assisting humanity. Saving a human being, doing something positive. That's what artificial intelligence and our machine learning tools should give to us and yield for us as well. But what I think Isaac Asimov and all of the scientific writers of that time really highlighted really positively was humanity's it was time for a change. It lit up the fires of desire for artificial intelligence. Unfortunately, many years before it can actually in reality happen properly. The idea of a concept robot like that, you can better get a robot to really use a Rubik's Cube properly, or make a cup of tea, let alone actually go find a human that's in danger and rescue them. But we're actually at the very early stages still of the information age. We're not even at the late stage. We're probably around about the middle of it. Hello there. Come on in. Must have been the gates locked. The gates locked. Yeah, so the information age, we're really only just getting into it. In the last 10 years, we've had the first big data products come out, which give us solutions to problems of big data. But big data only became a problem 15 years ago. Really, in reality, businesses had been sorting themselves out with current tools at that time. So this UCM talks about all of that. It talks about the pipe dream of the robots from the 1940s, 50s and 60s, but it also, unfortunately, talks about the AI winter that people have started talking about, where we don't have enough computing resources, we don't have enough data or technical know-how to create genuinely good artificial intelligence. There are bright lights out there, not to say there aren't, but there aren't that many bright lights. There's always a fail rate that attends with artificial intelligence. And I conclude with this as well, because actually, I'm afraid you're guinea pigs. This is actually almost like the first lecture that I'll be giving in the first week of October to level 6 students on the computer science degree, where I begin delivering machine learning and artificial intelligence module to them. And so this will be like the introductory lecture for that as well. So you may find me getting a bit stuck on the occasional slide. I apologise for that in advance, but I think it should go okay. So this is really, I'm afraid, this slightly out of focus monitor here. I'll try and read out what I need from this to you. This is actually a catalogue of what I consider to be the information age, given my understanding of technology markets. And it's actually understanding of where we have come from and where we are now, really, in terms of key juncture points in time. And so, come on in. So it's like a chronologue of where we've been in terms of technological creation as mankind. Here in the 1950s and 60s, the scientific authors were out there, the science fiction authors, they were creating this image of what the world might be in 100,000 years' time, depending on who the author was. That spun off some ideas. Academics, universities, businesses started producing computer-type technologies, started getting a bit better at it. 1968, the invention of the relational database. For those of you working in computer science, that's a database that's very heavily used in business today because it just works. In fact, the inventor of that database in 1968 became founder member of Intel, chip manufacturer. It all closely marries together. In the 1970s, it became the dawn of the computing age for businesses, but in that sense of not small desktop computers sat there, large mainframes doing big batch runs, doing simple jobs, a lot of them. So they would be managing accounts, creating very simple calculations, a lot of them, creating wage slips for very large companies. In the 1980s, we, Joe Public, started getting our hands on some of this kit. We've got the ZX80, Sinclair Tools, the ZX81, expecting smiles and faces of familiarity for what I'm talking about here, Commodore 64. And as we rolled through the 1980s, businesses started getting proper desktop machinery into their desks to do various jobs. They had proper accounting packages, word processing packages. But nowhere near started the information age at that time. We still had big data problems, but they were on just a different scale. We still don't have they didn't have the computer technology that you can think even 20 years, 30 years in, that AI was feasible on the machines. They all wanted it, and everyone was trying for it. And universities have been working at it for years. Still not enough computational space. So let's zoom into the 90s. 91, 92, Berners-Lee invented the internet, HTML. Key turning point for humankind and their use of information. Later on, Bill Gates, don't forget, by now we had Apple, we had Microsoft now in existence. Bill Gates wanted to build a Windows 95 to put a desk or computer in every desk, in every house, and every business in the world. He almost got there as well with Windows 95. A big change in the way we did things. We, the Joe Publics, gripped onto computers and started to enjoy using them. Our internet speeds, the fact we had internet was ace. I remember the first internet machine that I had in 1995. It was astounding what it could actually do. But it still wasn't enough. We still can't do AI with that. We can help ourselves understand the world a bit better, but that's about it. We move into the 1990s, the year 2000, the noughties, and suddenly broadband comes. With broadband comes a real attachment to the internet. It changed the way we believed that the world could be at that point, because information became so freely available. And of course, social networks proliferated in that environment. Google had to design itself so people could actually find stuff on the internet. Before Google, for the younger generations in here tonight, before Google, you had to know the web address. Yeah, so you got directory of web addresses, you had a computer magazine, oh, it's a new company, there's its web address, you type it in and find them. There was no Google pre-1998. Of course, that's all changed, it's just part of the fabric of it. But 2000s typified a big change in computing, because we now had global acceptance of computing as humanity. But then came the problems, the big data problems. Facebook, Google, first to encounter these really, where I think round about 2010, Facebook had 500 million global users, which meant it was dealing with petabytes of data on a daily basis, huge amounts of data. They built tools to support that, but with data comes the ability to harvest. Now, some of us might not like what I'm about to say, to harvest patterns in the way we behave and to predict what we're going to do next. And so those tools have always been in existence. During the 1990s, academics, the department I worked in, Centre for eScience at Lancaster, they were very heavily involved in the development of heterogeneous conditional logic models, which were models which used vast amounts of data in grid computing environments to harvest patterns that the human would never ever detect or see. And of course, they fell into the hands of the big global players, Facebook, Google, because they had this big data, and those models worked really well in that environment, and they had grid computing, masses of computers tied together that could do complex analytics for them. And they were generous. We might think of what they do in terms of harvesting patterns out of the data, but they're actually generous companies in some sense because they gave the world those tools. All of the big data tools that are commonly used in all businesses, even the ones sold by Microsoft, by Amazon Web Services, they were designed and created by Google, Facebook, and the big companies, social media companies, and they give it away for free as part of an Apache framework called the Hadoop ecosystem. That in itself means that no business now has a big data problem. There's a solution that they can take on board from that. And that also means the doors are now open to analytics of big data. None of the tooling that we use in academia to run what I'll define in a minute as machine learning or as artificial intelligence, none of that tooling costs any money anymore. It's free. It's given away. All the big data solutions, all the analytical tools. I'm using a package called R on this machine. Some of you may have heard of it. It's all free. You just download it and use it, and it does all of the machine learning tooling. It does. You can even link it to the AI. The toolbox I've got over here is a Hadoop ecosystem cluster built by Ambari. And again, it does complex big data analytics when you need it to. And again, the only thing that cost me was that machine, which is about £1,000, and it gives me a full tested system that I can use with my students now. And so the world changed. And I think in a negative and a positive way, all at the same time. And I say the last two slides I give is about ethics, so I'm not going to skip past that. That's going to be the end of this lecture, thinking about how do we control this information flow.
Ask Elon.
Yeah. So many people would have a view on it, to be honest, because there's so much stuff going on in this space. And because these tools are readily available, all of your data can be mined very easily, as I will describe to you. Now, in the 2010s, we call them that? I think it is, isn't it? In the 2010s, we actually have now this tooling available to us and all these statistical models. The machine learning tools come as instant libraries. We can run them in R or in a programming language called Python. Very extensively used in this field of data analytics. But machine learning at the moment is actually the age we're in. We're in the age of machine learning. We're not really in the age of artificial intelligence yet because, as I'll show you, the machine learning tools are a linchpin to artificial intelligence. They're very good, and now we're using them in big data environments. We're using these what are called heterogeneous estimation models. They do produce very good models, but they're not reliable enough to create AI that will try and save your life yet. And that's what I'm really trying to say. That will come in time, but it's not yet, and we don't know how long that will be. So, machine learning is the development and application of algorithms designed to uncover patterns in data. A lot of the stuff you may have studied in your past, if you've ever looked at anything statistical, if you've heard of things called regression modelling and things like that, they're machine learning tools now. They weren't when I learned how to use them, we just called them regression. So machine learning is actually a tool set which enables us to predict something new from a patch of data that we've got in front of us. It's an algorithm. It's pre-packaged mostly. You can program your own, and so it's a heck of a task. But they come pre-packaged, and you can do all sorts of different things with them. But they provide a sensory input to a computer system, which will eventually be an AI system. So think of that. We have these tools that harvest patterns from the data. They create a way of using that information that it creates, and then hopefully the computer will take a decision based on the information that it learns from it. There are, that would be that. When we have a machine learning algorithm embedded in a computer system, it's said to be artificially intelligent, although we have to use that a little bit sketchily, I think. So artificial intelligence is juxtaposed to that, actually, because it's like a system is said to be artificially intelligent when it's able to perceive its surroundings. And it's able to actually take some information from the outside and do something with it. So our machine learning tools are actually a natural embodiment of that. They are the eyes and ears of the computer technology we are trying to create right now. And when they get that information coming in, then they take some incoming actions to actually create some form of output. Now I've just given a bit of a fun three-liner up there. So I've got machine learning tools train computer to recognize patterns in images. So for example, a cat. How this would work is that I would have a library embedded in a computer system like that, and I would put in 20,000 images of, say, cats, and images without cats in, Our cat's doing all sorts of different things, playing with balls of wool, playing with balls, sitting on an owner's lap, cats in the typical sort of guises that they have, because they all look different. The things we take for granted as being able to identify a cat in a photo is actually really hard to do in computer world. And this is my point about the sensory inputs. They're just not there yet for AI. And I'll show you a project we're working on at the moment which kind of identifies that. And so I'd have to put my 10, 20, 30,000 images into the computer system and get my TensorFlow system to evaluate all of those. I will tell it of the information on the images that go in, what is a cat and what is not a cat. So it builds up a directory of all sorts of images, little numbers attached to it, and it then means when I actually get another image it's not seen before, I can put it into the system and it can compare it to what it's seen before. Say, I think there's a probability that that's a cat, and then it will tell me that that is a cat. And then it might do something useful, like go feed the cat, or rather, wake me up, send me a Twitter message, and then I'll go and feed the cat if the cat's been found. So that's the fundamental of AI and how it would work. This one I've just given as an example is just a computer vision of it. There are many other types of AI. I'm sorry, you can't read any of that. I checked it when I looked at the back before. I can barely read at my screen here, actually, because I'm reading a very small screen today. But this is actually a compendium of a lot of the different tools. It's not all of them, but a lot of the different tools that we actually have in this machine learning paradigm. That one I spoke about before is computer vision. It's becoming widespread and used actively in lots of different spaces. You'll have seen it used before. If you've got an Apple Pay, if you've got an Apple phone, you've got Apple Pay on it, you hold your card to it, and you put your Apple machine or your Apple phone to it, and it automatically reads the number with exactitude into your phone. That's computer vision. That's a very good version of it, by the way. It does work very well. Hello there. And so I won't go over that tool again because we've looked at that. I'm going to show you an example later on. But let me go through all of the various components that we've got there. The next one on the list is natural language processing tool. And so imagine you've got a Twitter feed coming in. You're an international business. You're getting 100,000 people talking about you every day in your Twitter feed. In the ideal world, you will have a sentiment analyzer analysing that data. And that's natural language processing system. And what that actually does is you give it a whole bunch of messages before you actually start using the model live, maybe 100,000 messages, and you tell it which of those messages have negative connotations to the business and positive connotations to the business. You throw it into the system, it does its analysis and builds up a back-end database of what it believes constitutes a positive and negative response. From a business perspective, this is important because if you've got a flow of Twitter messages and they suddenly go negative, you need to be alerted of that and you need a system to alert you to it. And so the machine learning tool, natural language processing, will actually enable you to do that. And you embed it into something like a big supercomputing cluster, which would then do the analysis for you and warn you when things are going wrong, or congratulate you if things are going right on the live feed of the text that's coming in. Further up from there, we have a recommender system. This was demonstrated actually at the Research Planning Conference back in July. And what it does, basically, imagine every website you've gone to for a very large company like Amazon, that kind of thing, and Netflix is another key player in this area. When you log in, it knows who you are. If you've made some ratings on some movies before, it'll actually run this recommender software in the background when you're fast asleep or maybe doing something else. And it'll recommend based on who you are, and it looks at you, and then it looks at everyone else and finds people just like you, and then sees what they have seen, and then tells you what they've seen, the bits you've not seen, and puts that on your screen. It's a recommender system. There's lots of different types of it. I've got one running here, actually. It's not running, it will run. And as I say, this is data-hungry stuff. I say this machine here, it's got 2 Xeon chips in it, 6 cores, 128 gigs of RAM. For those that are technically mind, you'll know what I mean. Don't worry if you don't know what it is. It was the most powerful machine I could build in 2012. And even, I'm going to run a little test. I'm not going to sit and watch it all the time. It takes too long. It takes about 7 to 8 minutes to run this particular test on it. And what it does is essentially estimates from a bunch of people, about 100,000 people, across about 1,000 movies, and estimates this model. It's what we call a sparse-based model in the sense that we have a table. I'll show you what it looks like actually when I'm in the model. We have a table that looks like that, and it's got holes in it. So what we've got here is people down here, obviously, and we've got movies across the right there, so we call it a sparse table. It's typical big data problem is how do you deal with the empty space? How do you work it in? And when you look at the empty spaces along here, what the machine has to do, all these are rating numbers, 2, 4, 5, the front row there, and the idea is, with these recommender systems, to fill in all the spaces with predictions of how that person would rate other types of movies based on what they've seen before and how that compares to other people. And so, imagine a data set. I think Netflix currently has 168 million customers, of which it has 5,000 movies on its database. That's an enormous table, an enormous amount of sparseness, and it will run a dedicated server just for that process. And it'll have 3 different types of recommenders. It'll have this type for ratings, it'll have a text recommender system, and then have some hybridization of the two as well that we'll be using for the predictions. So you always get something a bit different every time. And as I say, even on this, it's not high-end now, it's an old-end machine, but it's high-end in its day. When I run this, now bear in mind I have to fix it this afternoon, fingers crossed it will run. It'll just go ahead and churn away while I do some more talking about some of the tools that are out there. And this is your telltale about what it's actually like to work in the big data field. My AI is inevitably, or rather presently, not going to be quick. I'm actually running a data set which is probably about 300 megabytes in size. It's not massive, but it's got 27 million rows of data in it which it needs to work out. That means it's got something in the order of, I think it's 1.2 billion forecasts to create for each of the gaps that's in this particular file that I'm using here. But just let that run for a bit. It's going to be a while. It's still trying to sort the data out, spreading it out amongst the machine. So that was recommender systems and what they do. An important part of, you could almost imagine that in the robotic setting, couldn't you? Have you ever watched Red Dwarf? Yeah, the toaster. Are you sure you wouldn't like a bready object? And that's a recommender in operation there, trying to recommend something from a gadget, which is quite amusing. I mentioned before we have these things called regression models as well that work. I'm on the top petal here at the moment. Multiple types of that sit in that world. We've got linear regression, which is the standard stuff that we'll use. Very good for doing things like measuring consumer sensitivity to price changes. That's what I first cut my teeth on those when I started working for a company up in the north of Scotland. But then latterly I started using this thing called a logistic regression, which actually is much more useful in some sense because it actually enables us to estimate the probabilities of events happening given what we know of that event and be able to say, okay, what would be the thing that would increase the probability of that happening? So you almost think of this, how do I increase the likelihood of this person buying my product? And so the logistic regression would be a very good starting point to explore if you have enough data. Now, the last petal I'm going to talk about there is classification models. I'm going to swing over to this slide here. I've got a worked example I want to show to you, just to explain what that actually means. It's just a model I've used them quite a bit in the past, and they're quite good. If you think about what the term classification means, or clustering means, what it says is it takes a funnel of data, or a patch of data in the table, and you tell it what data to add to its algorithm, and what it tries to do is bring similar groups of those bits of data back. Yeah. In the marketing world, we'll be trying to bring back similar groups of people with similar behaviour that might be marketed the same way. Yeah. So, in the example I've got here is much more linear. It's just comes straight out of R. Actually, it's one of the data sets that sits in there. This is the iris petal dimensions data set. There are 3 types of iris petals that have been evaluated in this data set. I wrote them down because I can't read them off that screen, and I'm not actually an iris specialist. Setosa, versicolor, and virginica. And those leaves have been measured across the width and across the length. And what you see here is I've actually created a graph and actually ensured that the machine puts different colours to each of the types. And as you can see, iris, they're all very different, aren't they? All different species are actually distinctly different. We kill each of one. This is a typical training data set when you're teaching someone how to do clustering because it just works. It will identify the clusters with exactitude. Because you can see there's very little ambiguity. The interesting bit here for clustering models when data is like this is actually the overlap between the blue and the green, where there is some overlap between the 2 different species. That's the hard bits to get right. But that's what the advanced clustering techniques actually work at. Now, I've actually built a use case on this for the Titanic disaster. That's an open source data set now, and you can get all of the data for all of the people that were on that tragic voyage back in, was it 1912? And you can use it for all sorts of different machine learning training purposes. A little bit morbid, but it actually does capture the attention of students quite well. It's legal to use, you can download it, and it's used in all the competitions in machine learning as well. And basically, we're saying, can classification or clustering, the K means clustering technique, can that actually help us identify the groups by their characteristic as to why they died? So we all have a priori about why people died on that journey. I think most of us probably have understood that there weren't enough lifeboats for everybody. So people had to take decisions on the fly. It's never expected to sink. It's meant to be the unsinkable boat. And so they thought just limiting the lifeboats would be a useful way to save a bit of space, probably get a few more passengers on. But some interesting facts came out from it. Of the 2,224 passengers, 68% of them died. It was an enormous tragedy on a massive scale. So I thought, well, what I'll do is a demonstration here. Let me run a cluster model. It's all been pre-generated. And actually, let's look and see, if I put 3 bits of information into it, can it actually identify to me usable clusters, as we call it, people of similar characteristic, and pick it out from the data and tell me actually what were the underlying causes for this particular survival or death rates. The cluster data that I've put into it to try and identify the different clusters, I've got FAIR, which kind of identifies that hypothesis, with were wealthy given better access to lifeboats, because I actually have the fare, I think it's in British pounds, for the entire journey, so I can use that as part of my clustering technique. I've got gender, and that is a chivalry question. I remember in my mother telling me of the disaster that a lot of the men gave up their seat in their lifeboats for women and children, and that was a normal passage, a normal thing. Yes, so let's explore that, see if that becomes a choice factor, a decision factor in survival for ladies. And then let's have a look at age and see if there's a link to age, because women often carry children, and I'm sure the chivalry would extend to putting children onto lifeboats as well, although that's untested as yet. So this is the results that have come out. It's done in this package called R. The data set's in R, by the way. You can all run this at home if you want to do it. Just download it, it's all free. So I've got 3 different artifacts. Top table, middle table and bottom table. I wish I had a pointer right now to point the detail, but I'll get by. The top table identifies 4 clusters, cluster 1, 2, 3 and 4, and that's what the data told me was the best rate size of clusters for this type of data. The actual table in the lower part there is gender of passenger. 0 is male, 1 is female, and the numbers just below values 1, 2, 3 and 4 represent the proportions of male or female that are represented in that cluster, and the lowest row there is the total number of cases within each cluster. So cluster 1 is very small, there's only 18 of them. Yeah? There's not many people attached to that. 66.7% female. Cluster 2, 86 people, it's a bit bigger. 59.3% of those were female in this cluster. I predict straight away, I have the results of course, but this is what my prediction was before I ran the model, was that we'd have much higher survival rates in those 2 clusters as a result of female attachment. There might be other reasons underlying we can look at as well. Clusters 3 and 4, we've got the reversal here. So fewer ladies were identified in those clusters. Look at the size of the clusters: 420 in cluster 3, 190 in cluster 4, and many more males, obviously. That's the way that system works. So clusters 1 and 2, female clusters, predominantly female clusters, and clusters 3 and 4, predominantly male clusters. Now let's have a look at the analysis down here. This is a chart of that information. Again, it's just produced in R. We have fare and age on this axis over here. So fare here, I'm presuming it's in British pounds. I should have checked that. But we have age here, which is obviously now our annual age range. So that means there's lots of children around and on the boat. I didn't count that, but there's quite a few. There's certainly a lot in the 0 to 20 years old. I gather there was a 2-month-old baby on the boat. That's the youngest passenger I've heard of. The actual different colours represent the different clusters. So, dark blue is cluster 1. So that's the one with a small number of 18. They're the high fare payers. No real relationship to age there as such. They're the very top ones. They've obviously paid more than £200 per ticket. So they're probably the first class ticket holders. Below that we have cluster 2. And lo and behold, they look to be all of the second class ticket holders in terms of the amount of money. So now see what the clustering algorithm is doing here. It's identifying from the data the different clusters, and it's showing me that basically they represent different things in different parts of the actual model. And now let's have a look at cluster 3 and 4, which is the light blue is cluster 4, and the slightly darker blue is cluster 3, and it represents those en masse across the lower scale here. But it's interesting that it actually split cluster 3 and 4 in half. It didn't just say cluster 3 was adequate, it actually thinks there's a difference between those two clusters. So I've got these clusters, which represent very well on graphs. It pulls out different characteristic groups for each one, which is the ideal, is what marketers look for when they're looking at this from a marketing perspective. But let's have a look at what the final outcome is in terms of who actually survived within those clusters, because there are predictions that come out. The wealthy survived, and those females had a higher rate of survival as well. Those in the lower classes had a much higher death rate, unfortunately. And this lower artifact here actually suggests that to us. And this is the actual data. We have that in the data set as well. So 0 means did not survive, 1 means survived. Clusters 1 and 2. Clusters 1 had a 77.8% survival rate, which is kind of as we would have predicted. And Cluster 2 had a 72% survival rate. Cluster 3 had a survival rate of 33%, and Cluster 4 40%. So the actual technique, now this is a very simple technique, I can visualize the data. Generally in big data problems you can't. I've applied that type of technique to marketing type data before, and it does pull out valid usable clusters, and you can use it in a live data environment quite easily. It's not hard to do. It's not even particularly data hungry, to be honest. But it shows, this is when we hear people talking about classification and clustering algorithms, this is what they're doing in the background. They're trying to take you and I, work out our behavioural characteristics and something that's happened to us, and then bring us into these usable groups, the survivalists, the non-survivalists in this particular case. That's what it does. It tells us the scale of that issue as well. So there's an introduction to what that is. Let's have a quick look at our recommender system. Is that still running? Here's the data set. It does a count. When you start working on data of this size, actually, remember this is back to recommending people for movies. This is the actual data set size. Here's the number of rows. It's 27.75 million rows. What it's actually doing, it's going through and trying to work out its finished. Good, yeah. Took 7.8 minutes to create it. I have a user ID tucked in here. So this user has been recommended the best movies in the choice based on what the data provides. And so there's now a new table being created, one for every single user in the system. It will now be live in the system. That table will be fully populated now, basically. Now, how business will use that, they don't run that every time you log into the Netflix website. That'd be too burdensome. They estimate these models maybe once a day, once an hour, or something like that. Then they update the table based on what the current recent activity is doing. And so, that's how they get around it. That makes Netflix look nice and artificially intelligent, doesn't it? Sort of. We've all had those instances where it advertises things, teams say, why would I ever want to watch that? That's the importance of machine learning is it's not perfect. It makes mistakes very easily, actually. Now let's have a look at some live projects, because we actually have two machine learning projects in play at the moment. One of them centres around computer vision. We've got a chap, I hope he would be here tonight actually, but he said he might not be able to attend. Callum Staley, you may have heard of him. He does photography for the TT. Recently received an award from Michael Dunlop for the assistance in Dan Mean's creation of Dan Mean's calendar that was sold to raise money, and obviously an avid TT fan. Now, this is a computer vision project. In TT Week, he takes 10,000 photographs, of race bikes, and each photograph he has to go through and change what we call the metadata that attaches to it. He has to put in the rider name, the race, the lap, the bike, that kind of thing. And that's extremely time consuming. Every photographer you see does the same thing. And so the concept was that he wanted to develop a system of machine learning tools that would take a photograph, auto-load that up into the cloud, and then develop, learn from that image there basically what the bike is, what the lap is, what even the corner of the course is, and then that can be used for various different purposes that you would use it for. Here's the problem space. Remember what I said about cats? You've got to give a computer vision system lots of photographs of lots of cats doing lots of different things, different coloured cats. The whole thing has to go into the system that's going to be reliable. you have to do the same thing for bikes as well. So we were in test with this to see how many photographs it actually takes for the system to identify, A, that's a bike, and I can't see from there what the number is because that image isn't very good, number 4, and from there it would have to call back to a database and then work out, put that into the actual, the metadata of the photograph. The problem is, these tools that we're currently using in TensorFlow have limitations. All images have to be the right size and the right imaging and the right shape to be put into it. So that means every photograph has to be processed on the fly. When you're taking 10,000 photographs, that probably equates to 700 in a race. That's a lot of computational time that you have to think about. It has to be done live and on the fly as it happens. Because photograph, image goes up, photograph, image goes up. The problem is, as we've worked it out so far, there's so much noise in a photograph like that, or like that, or like that. You can't quite detect whether it's a motorcycle or a sidecar. So the first task is not to try and get it to identify the bike or the number. The first task actually is, what sort of bike is it? Yeah? Is it a sidecar or a bike? And so the first training hurdle is to sort that out. When it gets to that point, then it has to crop the image just so it looks at just the bike. There might be 2 bikes, 3 bikes. You can see the complications developing here. And then it has to blow that up to try and ascertain the number and the colour of the plate of the machine. Now, that's in test at the moment. Callum's doing an awesome job and spending a lot of time doing it for his dissertation project, third-year degree dissertation. And I hope it works for him because he's put loads of blood and soul into it. He really has. And but a very good tool set. There's no reason why it shouldn't work. We were talking about it yesterday because we've seen good computer vision tools being used, and I mentioned before the credit card pickup on Apple Pay works extremely well. Whether or not they have their own proprietary libraries, tools and technologies that makes that work for them, we don't know. But we hope that'll work for Callum because it's a time saver, a massive time saver to be able to do that. The other project is one of my own personal projects. Back in September, I began building crypto trading bots because I needed to get my teeth into something that was AI related. And as it turned out, I spent a month and a half building some bots that are now trading live on crypto markets on the Binance exchange. It wasn't because I wanted to become a crypto millionaire. I got a couple $100 running. Okay, so it's really about the building of the technology and to work out how it can be done. I have another level 6 student, Liam Gregson, that's actually building an app for me because we kind of got thinking about how do we present this information to people from the bots. And it's a bit of a sideline, that really, but it means basically if we get it right, we might be able to sell this as a technology somehow. Because if we can work out the correct way of predicting what the market's going to do next and buy accordingly, we can make a little bit of money on the side of it. You never know. But that's actually not my ambition right now. I think it's a bit of a dream. There is my background is originally an economist. My first degrees are economics, and currency forecasting was an interest area of mine. And it is almost impossible to forecast a market in the longer term, but actually in the shorter term there are patterns you can take advantage of. 80% of trades fail and don't succeed to be profitable. Your aim is to obviously consistently be above that and be in the remaining 20% that do make money. So these trading bots trade 24 hours a day, 7 days a week. They don't sleep, they don't need paying. They cost me about €10 a month to run off a server in Germany. And they do the job, but the problem is they're not perfect. They have lost me money, not a lot. Annoyingly, about $100. It's more annoying than anything else for the effort I've put in. But the idea is now, the next stage is to build AI into that system and say, right, okay, we know what machine learning tools do now. What they do essentially is they summarise activities and then make forecasts as to what should happen next. So I've recorded every single trade that I've made. I think I'm up to about 1,700 in and out trades now. So I've got quite a bit of data to work with, and the idea now is to build a logistic regression model which estimates the probability of those trades actually being incorrect. So that says, right, okay, that's fine. The bot wants to trade, and it goes through this machine learning filter, and it says, no, probability is too high that you're not going to succeed. And then it shelves that trade and just waits for the next opportunity to come along. And I'm also going to run that alongside a neural network as an alternative way of estimating the probability. And it's just a fun project. It really is fun working with this live, high-speed data because it actually gets you to think about how you construct your databases because there's a lot of data that comes in, 40 or 50 trades a second on some days if the market's really busy. So you have to learn how to deal with that as well, which has been very interesting. But I'm hoping to present the results of that Gala, is it September we've got the Research Festival? Yeah. So,
The 18th, thank you.
Yeah. So
External director.
yeah, I'm hoping to have the results of that project out,
Excellent.
and possibly Callum's as well, if he wants to present that for us as well. So we'll just see how that worked out. Both of these, obviously, all three of these are actually use cases for the delivery of the module that I intend to deliver. And as I say, I'm going to be the dark force of AI and say it's not there yet. Don't worry, we're still working on the machine learning bits at the moment. What you get to used to when you're working with machine learning models is they have an error rate. Yeah, they do things that are not quite right. And this recommender model is finished, and I'll show you what that actually means. There should be a value in here called a mean square error, RMSE. There it is. Yep, that value there. It's a value. It's a meaningless value. In rating systems, it has an actual meaning. 0.83. It means basically, if a person makes a rating of 3 on a movie, plus or minus 0.83 is actually the wide scale. When you make a forecast of 3, it could be plus or minus 1 near. Yeah, that's quite a wide range on the scale rating system of 5. Yeah? And so there's an error rate. This is why Netflix doesn't always get it right when you log in. It shows you movies you're not that interested in. It's because they have a degree of ineffectiveness, a proportion of ineffectiveness. There's another sentiment analyzer. There's a sentiment analyzer there. I'll show you. That's actually a lot better. Oh, sorry, wrong machine. Go around onto ethics. So let's have a look at the sentiment analyzer here. I've not run this yet. Actually, let me run it. It takes about 20 seconds. Now, what this is movie ratings, text-based. So you know those short ratings that people put on Netflix and stuff. And so this is talking, Brokeback Mountain really sucked. Yeah, actually, we talked about how Harry Potter sucked. And the Da Vinci Code is awesome. So we're into sentiment analytics here. So we tell the machine we give it. I think in this case we gave it totally 7,000 reviews. The number estimated somewhere. Yeah, there it is. 7,087 reviews. We hold back about 20% of them and give it the remainder to work on. And then we throw in and we tell it what's a good review, what's a negative review. And then we set that against the data we didn't give it to do the estimation on, call it holdout sample. And that then tells us how precise the forecast was. So in this case, percent correct is almost 99% for the holdout. So actually, there's a machine learning algorithm that actually works. The NLP stuff, natural language processing, is actually really quite good now. I put a video on YouTube relating to Ambari from my students back on the 30th of December, and if it's still live, there it is there. It's actually transcribed what I've said on the YouTube video, and so it's actually done a really good job of it. So it's taken my YouTube video, and over the last month, I only saw it here this morning. It's quite good timing, really. And if you read it, it's word for word. It's not good at punctuation. That's the bit that I'll say it lacks. But I speak, you've heard me speak now 45 minutes, and it's like I tend to speak in a quick way. Maybe it doesn't pick up full stops and commas. But actually, it's apart from the complex technical stuff, it's got it 100% right almost. So NLP is there. Watch out what you say when you've got your phone in your room if it's something a bit dodgy. Okay. And therein lies the rub, really, with all of this stuff, which is, where do we go next? Well, I've got a module to run, which is basically what you've seen there, parts of it. There'll be other stuff put into it. Yeah, I'll be using some of these tools here, R data analysis training. This is what we've got now. Yeah, I'm going to be developing a module using some of the tools that you've seen here before. None of it's perfect right now in terms of what the tooling is, and mistakes are made. The tools we're actually going to use for this are going to be our data analytics tool training. We deliver that already at level 4. Level 4 already get a data analytics module for 12 weeks, which looks at the core data analytics up to an elementary machine learning and regression. We also teach big data training, provide big data training to level 5 at level 5 for about 6 weeks to give them an introduction to this kind of stuff here and what it does. And now we have the big module coming, which is going to be really hard to do actually, which is machine learning and artificial intelligence, which I'm quite looking forward to with a bit of trepidation, because one thing I didn't tell you, when you're building a model like that for a company, it takes about 8 weeks to build it. Yeah? Once it's there, it just runs and runs however many times you want. You know, coding is like Nick. It's just like it can be a pain. And so when you're taking a brand new business problem, you're running an algorithm into it, you'll find breaks in the data you didn't expect. The data won't be in the right shape. And that also means a module like this takes time to build as well. And it also means you have to really start thinking about the ethics of this game. Everyone here has heard insulting stuff about machine learning and how it's applied to people's data, things that they don't like. In the press this week, there must be about 5 or 6 stories of negative press relating to even authorities' misuse of data. I don't know whether you heard the news story in Germany. They're trying to kill, in Europe actually, they're trying to kill facial recognition technology before it gets going because they don't understand the ethical implications of what we do. It's important that we think of the ethics at the core of everything we do with data analytics. Even today, we have UK police using facial recognition in parts of metropolitan London to try and identify criminals. If it was 100% successful, it probably wouldn't be so bad, but it means you were walking through town and you're being scanned and you've been databased. Yeah, and then your image can be used anywhere else. Now, they apparently have rules and regulations to limit how that's used, whether it's applied or not. But even though the government's saying, please don't do it, the Met's carrying on doing it. And so there's kind of like an ethical comment there about how that's applied. Now, the problem is not, there's a university analyst that was asked to look at it and think about why it was a problem. And he said, it's the problem of false positives, and that's a common term in machine learning, which is, I can make a prediction, and I can put you all through a spatial scanner, maybe 1 in 100 people be falsely nabbed by the police and being accused of somebody he or she isn't. And those false positives, it's not really ethical to be evaluating your entire legally existing citizens. It's just not really morally good to do that. Now, I'm just trying to find... So I'm going to follow Google DeepMind in this. They're actually quite good. I'm treating it a little bit of care. They're actually building a team of academics, business leaders, and various other people from the communities. And they're going to be trying to lead the way into how data should be used. Now, that sounds dangerous coming from Google, one of the big data owners, but we need to start from some point somewhere. Millennials in the room, and those rest of us, we're going to be impacted by this machine learning and artificial intelligence really closely. Rapid expansion of it in your lifetime. I delivered a module this year on emerging markets, and it forced me to think about the information age and where the future will be. And it forces you to think about, every time there's a big change in technology, there's a group of people that get disadvantaged by it. It's just automatic, it's what happens. Henry Ford built the first mass-produced car plant. All the engineers became mundane engine stampers. Yeah, they just were part of the machine at that point, rather than dedicated engine builders. So that kind of way of thinking. And this tool set is going to do the same thing. And I have 100% certainty there'll be no need for lecturers in anywhere between 50 and 100 years. Whether we think that's a good idea, I don't know. So, ethics will be considered solidly, and we're just going to have to see how that spins out when this module actually starts moving forward. I'll take any questions now if you have any, though. Sorry, I've lost a slide here. Now, this is cloud service for you. I've saved it on another machine and it's not updated it. There's a slide I was getting ready for, which I fluffed up a little bit there. But I'll take any questions if you have any, please. Yes?
I was just wondering, because I know probably of Grammarly, I was just wondering what type of machine learning that would use.
Is that Grammarly, did you say?
Yeah.
Yeah, it will use one of text binders, I suppose. It's only text-based, isn't it? So you're actually typing something live on a machine, and then it's just putting a correction up for you. And so it'll be looking, unfortunately, looking at faults in your text, and it'll have a background of data stored somewhere, and it'll just put that correction to you. So yes, if you like that natural language processing system. Is that part of the assignment?
No,
Any other questions?
On your on the motorcycle one,
Yeah.
why did you change it first to identify the bike? I thought it would be easier to identify the plate.
No, we thought that. It's to do with the way it scales the photographs down. So photographs, when you're a professional, you might know this, but when you're a professional photographer, you're into big scale an image, 12, 14 megapixel, but actually the typical libraries can't take that much data, so you actually have to scale them right down, and when you do that, you lose all the definition of the small byte. If you look at an image, it might be, where is it now? There it is, there. If you look at that, it's probably Dean Harrison looking at the colours there, it's probably only about 20% of the image size. It's good for us to visualize it and to see it, but for a machine learning tool, it needs to see more of it and to bring it out. But the advantage of having this big image is you can crop out, if you can find the bike, then blow it up, and then you should have a bigger image on that plate, because you've got the pixelation to deal with anyway.
So there was more processing power and more speed and all that, and might be.
It'll be doable. I don't think there's a problem with it being doable. I think it's doable. It's just, whenever you're doing any data analytics of this type, data science type stuff, every problem is different, and you end up, the time it takes to actually start using the algorithm is actually the time to get the data in the right shape for the algorithm. Yeah, you do this stuff. But it's actually more complicated. I did a job for a company over last summer. It was just 7 weeks to put the data into the right shape, and for the algorithm to actually touch it. And that's bringing data in from lots of different sources and munging it together and just trying to meld it into something else that it will use. But it's the same with this. So if I were to do the cat, if you look at all the test imaging that you find online to do with cats and putting it through imaging systems, they're all standardised, they're all the same size, they're all dead easy to use, and that's what we train with, but actually when you're confronted with the real stuff, it's actually a lot harder. And also, bites have different angles.
It was why I thought the plate would be easier.
Yeah. Any other questions? Yes?
With emailing and stuff like that, so say if you're on Gmail and you get an email from someone, does it use machine learning to identify, because you get little text boxes that say generally like appropriate responses to what's being said in emails, does that use machine learning to...
I don't think I've seen that. So can you explain what that is?
So you receive an email from someone, just be giving you like a piece of information, and I'll say like, here you go. And when you go to type back, you press the reply button, and it'll have little boxes saying like, okay, thanks, or...
I need to update my computer system. Right. Yes, that will do that. That's almost similar to... it's giving you a recommended set of responses to the question.
Another example would be when you book a flight and you get the confirmation email and say, do you want me to put this into your calendar for you? It's recognised that you're doing something on that day.
These are all interesting cases. They're actually relatively straightforward to do. You can recognise things writing you see Apple stuff doing it all the time. So you're typing the data, then it's being on that data into your calendar. And it's actually relatively straightforward to do that. It's only a small bit of text. That's the neat stuff. I tell you what I came across when I was putting slides together for another lecture was with a new feature that was going to PowerPoint, and it was clever. And so I'll come in. And it was actually really clever. I was quite impressed with it. These are the niceties. This is the computers helping humans do things in a nice, neat way. And I built a slide. It's to do with Hadoop service clusters. And one was talking about Hadoop, one was talking about databases, and the other was talking about distributed computing. They all kind of talk together. 3 different paragraphs. And this design feature, by the way, would you like a new design for this slide? Right, let's try this. I'm a bit sceptical. But for a whole host of different designs, and it actually managed to map the images to the sentiment of the text that I've written. So natural language processing is actually pretty good, to be honest. It does work. And actually, a lot of the slides you've seen today were built that way. I usually do very mundane slides. I'm guilty as charged for that. And then these... Not that one. That one there was, actually. I would just normally place my image somewhere in there, but it said, would you like to look at it this way? It hadn't done any of the fancy stuff I showed you at my other lecture, but it could easily have done. That was fancy pants as well, there, and so was that. So from there, I didn't choose that image. It said, this is the image you want for this. Off you go. And it fits okay to the theme. It's electronically based. Could have put a robot in there, I suppose, but I was quite happy. Any other questions? Yes.
To me, to like the diagram sounds good. You have some clear classification based on gender and phenotype. So you have a clear intuition about what you were looking for before you found the information.
Yeah.
So compared to the trading example, how much of an intuition do you have about risk models in trade models.
Oh, no, that's something I need to learn.
So do you have the algorithms that suggest the class and you calibrate this class model?
No,
And then you
I
trade
don't. All I have is how logistic regression works is I have a model that works or doesn't work. And I have a whole host of market data which I've collected that attaches to that. So it's what the profit and loss. So I have all the information at the time of the initial trade and whether or not that trade was successful or not.
So
And that forms a 1-0 binary. And what logistic regression does, if my model works, that's still going to be tested, it actually works like a regression model, and it'll estimate for me the actual probability that the next trade, based on that similar market information, would be negative or not.
Right, but we must have a risk model. You must have a sense of framework how you measure.
Well, I don't. I've been doing this for I haven't looked at my models now. I did a month's work, 6 weeks' work, and my model's not looked at them since. I just wanted something I was running to gather some data, but no, I've not run to that level of detail.
You see, the trick with these things is actually identifying what to put in your model.
Correct.
So I know of a company, a financial services company, that is trying a concept and trying to almost work out a credit score, but they're not using it as the only indicator. So what they do is they feed the client information in.
Yeah.
And then they look and see what kind of credit score they're getting from that model. And then they're comparing it to their normal score in the system. And now they're looking at potentially combining the two to get to a thing. And what they're seeing is, the more information that they're actually adding to that model, they're getting very interesting results, because now your model's looking at data that you typically wouldn't use. And sometimes it's useful, and sometimes it isn't.
Yeah. It is, and it's a game of experimentation. This is where this is one of the key points for AI is we want robots to be self-learning and self-creating. They can't do it at the current state the way that we do data analytics because it's too complicated. They would spend more time trying to work out which model and testing lots of different things. Like you were just saying there, Nick, it's that you need that human element involved to actually say, you're wrong, the market doesn't evolve with this, it evolves with this and that tied together. Things that actually a robot wouldn't know what are, and AI device wouldn't necessarily have intuition about.
They do have non-guided machine learning now, some small data.
Yeah, you can do it, but what I'm saying, imagine a big problem. I'm a business, and I've got a large amount of data. This is what's the current state. You have some automated algorithms that are going out there and mining the data. And what they're doing, they're trying to find associations between different data panels within the organisation, associations and relationships. They can't really do anything with that themselves, because they don't know, the machines themselves don't really know if that's real or not. All they can do is give them to an analyst to do a final reckoning on. It's minimising the time of doing the search, and it's stopping the analyst trawling all of the data. And it's very nascent. It's actually quite advanced to be able to do it. Some of the biggest companies will be doing it, mid-size, no chance. But yes, there is an element of automation that can happen in it, but very specific use cases, I suspect. But when you come to do stuff like that, if you're a unique business with your own unique product portfolio, that model might work for a movie. It might not work for another company selling movies of a different type, and that needs to be evaluated by the analyst, and that takes time. That's where the time comes from. What data have you got? How do you move it into space? What's the best way of modelling it to get the best predictions out of the model? It isn't straightforward. I've learnt that in the last 2 years doing it. And it was a lot easier 15 years ago. I was writing papers on this stuff because we had 2,000 rows of data. We planned the collections ourselves to map into the models. These days, you've just got a huge amount of data, and you're trying to fit models to data to see if it works. And it's actually very different. We wouldn't have done that in academia 15 years ago. That wasn't the right way to do it. But when you have vast amounts of data, it's the only way you can do it. But it's time-consuming to sift and trawl through all of this stuff. And I say there's no perfection, and I kind of do stand by my... you're safe from dangerous AI right now. The slide I've lost, that's what threw me there. Really annoying. There's actually, you should take a look at it, because there are some ethical considerations in all of this, absolutely. And there was a University of Vermont activity which I wasn't comfortable with. Now, universities do have strong ethics divisions usually, but they had actually built a model of a living device in the computer simulation world, then mapped it and got the computer to build it using stem cells successfully, and built a living organism. Now, I look at the ethics of that and start thinking that's actually quite dangerous. You won't really know what the result of that is, in fairness. But they've been through an ethics panel. It's been funded probably by somebody in the United States to get that research done. But it's there now. Those are the things we need to watch out for. I think the level we're teaching at level 6 next year won't be a problem, the training data sets. But the students do need to be aware of how they use our data in the future, because these students will be out in the Isle of Man using Manx data at some point. And we just have to be a little bit careful about that.
So that famous mistake that Microsoft made with the first visual system on this, it had racism.
Oh yes.
Stuff built in.
Yeah. Mistakes, fundamental errors, untested systems, and things like that. Well, we don't know how the photograph thing will go there, but we do have permission to use the photographs, by the way. We spoke to the TT and they were happy for us to do the study. So we've not broken that rule. And it can't do any harm, really. You know, it's one of those, it can't do any harm. And the fundamental rule of computing is do no harm. So, but some of these other projects, we do have to be careful. Because of our data so widely out there and there's so much of it, it can be abused. And that's what we'll have to watch out for.
How worried are you of the 5G?
I would like to see the studies which indicate health may be a problem, and just see how reliable those studies are, or whether or not enough study has been done on it. And we seem to be railroaded into it right now. It seems to be that is what we're going to be doing. I've not studied the academic journals to find out actually what the research is like and how reliable the results are.
In the proposition end of the data that people are taking, it's going to take over people's jobs and careers.
Yeah.
How much energy are we pumping into ethical values?
How much energy we put into
ethics or other morals?
Yeah, that's another part to be explored.
What's the percentage of ethics using? What kind of energy are we putting into ethics, or are we just...
Ethics, I'll let you know how we do it. For all of our dissertation projects at the university here, go through an ethics panel. What we mean by that, the students, from a computer science perspective, they have to complete an ethics, which even involves social implications.
An ethics panel to me, because...
Well, no, we have it at Chester University, who supply our degrees, but we do that here as well. I wear the ethics chair. I stop projects I don't like, so we don't let students, for example, work on disadvantaged people, very young people, things like that, because it just creates too much of a problem down the line with data collections.
We were at one of the first lectures where we were about automated transport systems.
Yeah.
And we saw the data that they're requiring to get rid of taxi drivers and bus drivers. And the ethics of that is phenomenal.
It's funny where you...
18 million jobs in the next decade.
Yeah, this is where we actually ask our students on our ethics forum to actually, what are the social implications of the technology you're creating in case it has an impact like that, be able to think of that. But unfortunately, developments in computer science are all about that.
Yeah, I hate to say.
Yeah, it's all about that. It's automation. It's automation.
Where do you draw the line?
I've already put my career on the line and said, one day I won't be here. There will be a robot who's far better than me. Just plug in all the chips for all the degrees and just know everything. You know, that's going to happen.
Teaching has never changed. We've always had students here as always a guy like that.
Yeah, but that will change. Yeah, that will. I get tired. Yeah, that's right. Exactly. YouTube tells you everything anyway. There was definitely that case to say that's a problem. There will always be disadvantaged groups. Like I say, this module on emerging markets, it was really good for me because it got me to think of the philosophy of change and what it means, because every time there's change, it implements a group negatively. And as I say, that's just common. What, sorry?
They're fatalistic in their viewpoint. AI is getting bigger and bigger. It's always fatalistic.
It is. Hopefully I laid it by just saying the models aren't great yet. But that they will get better. Yeah. There are teams of people in academia and beyond that are working on these models to make them as good as possible. We're talking big data now, terascale, petascale data. In 10 years' time, it's going to be 10 times bigger than that, and they will have much more data to use and much more processing power, and they will get to that dream of producing models at work. It will happen. Whether it's 10 years, 20 times, 30 years, I'm certain it'll happen, because I know what it was like 15 years ago.
Those private companies just outsource government companies. Government's being left behind.
Well, maybe that could be the Manx case, certainly not the UK. The UK government was funding e-science, quite a considerable sum for many, many years to make sure grid computing skills were available in the United Kingdom. I don't know where that sits for the Isle of Man government. They have their own ways of doing things.
Yeah, I mean, if you look at the US, like Peter Thiel, who's very close with Trump, they just recently it was leaked, but us, which is this controversial project about, the illegal immigrants in the US, they're using data models like this to find and, deal with the problem. That kind of sounding multi.
Well, recently that the government has tied up a deal, I think it was with Microsoft, to conduct all of their big data work. So they'll be going to the Azure service, that's all CIA military stuff. That's going into one of those, but on a huge global scale. And that is going to be used for that automatic finding of patterns in data for all its population and all the enemies and things like that. Well, this is where the role of ethics, we can't control that. It's too big for us. Yeah, it's out of our hands. British government will be doing it too. They just haven't told anyone about it. What do my friends at home say? Just don't use the internet. You'll be safe. That's where the data comes from.
I suspect that's too late for all of us.
Yeah, I know.
That would nice. Ali, thank you so much. I am the greater unwashed in the technicalities of this topic, but I really enjoyed the presentation, and particularly when the Titanic, one of those examples that brings to life the power and the capacity of this stuff. Ethics. At UCM, we've got a control on ethics. Any research our students done, as Ali said, is control, but we're right to be cautious in the bigger picture, I would imagine. We need to leave. I'm sure Ali will hang around and do
well, I'm going to unplug this
as we walk slowly out. But thank you very much for coming. If you like this debate, you should tell us, and we'll perhaps it's a debate. One of the things we need more debates, don't we? One of the things I'm thinking at the end of our UCM talk to is that we might actually have a debate, and it could well be the ethics of these sorts of topics, because that's the bit that
it's actually a really good idea.
Going for and whatever. So we'll keep us posted, and obviously everything we do is on the UCM website. As is our next talk, which is complete change of pace, but it's the latest research around the effectiveness of cancer treatments. And we're very lucky to have Dr. Ken Mills from Queen's University Belfast, who's one of the UK's leading researchers in this area, and that's on the 19th of February. Same time, same place. Thanks for coming, and thank you, Ali.